On December 25, 2021, the James Webb Space Telescope was successfully launched aboard an Ariane 5 rocket from the European spaceport in French Guiana. Its primary objective was to gather data about the universe that Earth-based observatories cannot access. However, not all the information it has sent back has been reassuring. Webb has detected over 200 unidentified forces or objects traveling through space, and the nature of these anomalies has raised global concern. When observed from afar, the Milky Way presents itself as an immense spiral galaxy. Approximately 100,000 light-years across, its characteristic spiral pattern is formed by stars and gas rotating slowly over immense spans of time, giving it a pinwheel-like appearance. However, a closer look reveals that individual stars within this galactic spiral each follow unique paths. It's similar to a crowd of people generally moving in the same direction, but each at their own speed and along separate routes. The stars don't move in a uniform pattern. Instead, their motion is governed by the galaxy's gravitational forces, which determine the trajectory of each star. Gravity drives these stellar movements, with the mass of the Milky Way shaping the paths of stars in a wide variety of forms. Some stars near the dense galactic center follow nearly circular orbits, while others further out move in more stretched elliptical paths. The amount and distribution of mass in different regions of the galaxy affect the gravitational pull on each star, altering its speed and path accordingly. This complex interplay of forces forms a dynamic system, where gravity acts as the main architect of the galaxy's structure and evolution. By examining how stars orbit in the galaxy, astronomers gain valuable insight into its overall stability and development over billions of years. However, observing the exact paths of individual stars is no easy task. The vast distances involved and the limits of current observational tools pose serious challenges. To overcome this, scientists rely heavily on advanced computer simulations, which use physical laws and observational data to model the motion of stars across the Milky Way. Without such simulations, understanding the galaxy's behavior and changes over time would be nearly impossible. Despite all stars orbiting the galactic center, they do so at varying speeds, a phenomenon known as differential rotation. This means that stars closer to the center of the galaxy complete their orbits more quickly than those farther out. As a result, different parts of the Milky Way rotate at different rates. The varied distribution of mass across the galaxy, particularly around the central bulge, contributes significantly to these differences in orbital velocity. Investigating this complex rotational behavior is crucial for understanding how mass and gravity interact on a galactic scale. The spiral arms of the Milky Way are shaped by density waves, gravitational disturbances that move through the galactic disk, causing material like gas and dust to compress in certain areas. These compressed regions become fertile grounds for star formation, often giving rise to bright clusters known as stellar nurseries. As stars and gas move through the galaxy, they encounter these waves, leading to patterns of accumulation and dispersion that continually reshape the structure of the spiral arms. The Milky Way contains a broad variety of stars, which contribute to its unique structure and behavior. Some areas harbor young, massive, and hot stars that burn brightly but live briefly. These stars are typically found in stellar nurseries within the spiral arms. Other regions are home to older, cooler, and longer-lived stars. These stars are more stable and often grouped in various types of clusters. Open clusters, composed of relatively young stars, loosely bound by gravity, and globular clusters, consisting of older stars densely packed in spherical arrangements, both orbit the galactic center. These stellar populations, with their differing lifespans and dynamics, play a vital role in shaping the galaxy's evolution. Among the most intriguing findings from Webb and other observatories is the detection of over-velocity stars, objects moving at extraordinary speeds, far exceeding the typical velocity of stars in our galaxy. Since their discovery in 2005, astronomers have sought to understand what could cause these stars to travel so fast. Their motion is believed to result from dramatic gravitational interactions, especially with extremely massive objects like supermassive black holes or through dynamic encounters in binary star systems. A primary suspect in these events is Sagittarius A*, the supermassive black hole at the center of the Milky Way. This black hole, with a mass millions of times that of the Sun, exerts a gravitational force strong enough to fling stars outward at high velocities. If a binary star system passes too close, the black hole may pull one star in while catapulting the other away, a phenomenon akin to a gravitational slingshot. Such rare and extreme events can eject stars at speeds that allow them to escape the Milky Way's gravitational hold. But supermassive black holes aren't the only mechanisms for producing hypervelocity stars. Events like supernovae, the explosive deaths of massive stars, can also impart enough energy to propel companion stars at tremendous speeds. In binary systems, complex gravitational interactions may be sufficient to eject one star. Dense star clusters, where stars are packed closely together, may also produce similar outcomes under specific conditions. Despite the varied origins, hypervelocity stars share some common traits. They are often exceptionally massive and luminous, traveling at minimum speeds of around 1.5 million miles per hour, well above the escape velocity of the Milky Way, which is approximately 1 million miles per hour. Previously, such stars have typically been traced back to the galactic center, reinforcing the theory of a gravitational slingshot from Sagittarius A*. However, when astronomers began to search for smaller stars, those similar to our Sun among these high-speed travelers, they found something unexpected. Using extensive data from the Sloan Digital Sky Survey, researchers identified stars with unusual motion patterns. Upon tracing their paths, they discovered that many of these stars did not originate from the galactic center, as expected. Instead, they appeared to come from random directions throughout space. Hypotheses suggesting origins in nearby galaxies like Andromeda were ruled out after further analysis. This raised new questions about the forces behind their high-speed TORIES. In parallel with these astronomical investigations, physicists studying the subatomic particle known as the muon at Fermilab in Batavia, Illinois, reported surprising results. Muons, which are similar to electrons but more massive, displayed a peculiar wobble when subjected to a magnetic field. This behavior deviated from predictions made by the standard model of particle physics, hinting at unknown particles or forces influencing their motion. The experiment revealed discrepancies between observed and expected results, suggesting that our current understanding of particle interactions may be incomplete. The experiment was conducted under extremely cold conditions, close to -450 degrees Fahrenheit, using a superconducting magnetic storage ring 50 feet in diameter. Muons were accelerated to near-light speeds and sent through this ring, where their interactions with other particles produced measurable effects. These interactions changed the way the muons wobbled, suggesting new physics beyond the standard model. Such findings, if validated, may eventually help explain some of the mysterious forces at play on a cosmic scale. While the James Webb Space Telescope continues probing the universe, it has also explored distant regions within our own solar system. One such area is the Kuiper Belt, a vast zone beyond Neptune, filled with dwarf planets and icy bodies. This region, often called the graveyard of the solar system, contains ancient celestial remnants that offer clues about the early stages of planetary formation. Bodies like Pluto, Haumea, Makemake, and Eris inhabit this zone, along with countless smaller Kuiper Belt objects, KBOs. These icy objects serve as time capsules from the solar system's infancy, preserving the original materials and conditions present billions of years ago. Scientists are especially interested in their chemical composition and internal activity, as some KBOs show geological or atmospheric changes despite the extreme cold. KBOs emit light in the infrared spectrum, which the James Webb Space Telescope is specifically designed to detect through infrared spectroscopy. JWST can analyze the chemical makeup of KBOs and detect features invisible to the human eye. Some of these distant objects exist in binary or multiple systems and may have rings or small moons. Their wide range of colors, shaped by composition, radiation exposure, and age, helps researchers categorize and study them. JWST is equipped with powerful tools for such observations. Instruments like the near-infrared camera, NIRCam, the near-infrared spectrograph, on our SPEC, and the mid-infrared instrument MIRI allow scientists to gather high-resolution data on the earliest galaxies, star-forming regions, exoplanets, and faint celestial bodies. The Fine Guidance Sensor FGS and Near-Infrared Imager and Slitless Spectrograph NIRIS ensure accurate alignment and enable broad-scope surveys beyond our galaxy. JWST also supports efforts to unravel the mystery of dark energy of force, believed to drive the accelerating expansion of the universe. In coordination with missions like Euclid, Webb's infrared capabilities will deepen our understanding of how dark energy operates across cosmic time and space.